Welcome to qnawire.
So now we'll work on problem 52 from chapter 20. In this problem, we're asked for each of the following reactions, write a balanced equation, calculate the standard EMF, calculate delta G at 298 Kelvin, and calculate the equilibrium constant at 298 Kelvin. So our first reaction is aqueous iodide ion oxidized I2 by mercury 2+. So we have this I minus aqueous ion, which is going to be oxidized by mercury 2+ to produce I2, and then the mercury will be reduced to neutral mercury, and there should be a 2 here as well to make 2 the iodine molecule. So we can look in Appendix E, and get the reduction potentials for these two half reactions. And so we'll put the reduction reaction first, so the reduction of mercury, and we get 0.79 minus 0.54, and that's equal to 0.25 volts. So that's our EMF. So then to calculate delta G, we need to know our equation is negative N Faraday's constant times this EMF. So this N here represents the number of electrons that are transferred. And since we see mercury 2 going to neutral mercury, we should say that there's 2 electrons transferred. So we have negative 2, then we have Faraday's constant, which is 96,485. The units for Faraday's constant are joules So then we need to multiply by the EMF which we just generated, which is 0.25. So here we multiply through and we get negative 2.34 times 10 to the 5th joules per mole, which is also equal to 234 kilojoules per mole. Either way is correct, but we'll need to use joules per mole to calculate the K value. So now our equation for K involves delta G being equal to negative RT ln of K. So if we flip this around to solve for ln of K, we get ln K is equal to delta G over RT negative. So here we can put so I actually wrote down the wrong number here for K. This here is for the next one, and I got them mixed up. So for the delta G for part A is negative 4.82 times 10 to the 4th, and this is negative 48.0. Yes. So delta G here we have this negative 4.8 times 10 to the 4th joule per mole divided by RT. So the value of R that we're going to use is 8.314 because it's in units of joules per Kelvin mole. And then we're going to multiply that by 298 Kelvin. And that gives a value of 19.47. So then the ln of this is equal to ln of k. So then k, if we take the inverse of the ln, or e, we get 2.86 times 10 to the 8th. So now we can move on to part B, where the reaction which we're looking at is an acidic solution. In acidic solution, copper 1 ion is oxidized to copper 2 by nitrate ion. So we have copper 1 Cu plus nitrate, and then we're in acidic solution, so we have protons present, and it's copper 1 is being oxidized to copper 2 plus NO and water. So now we can balance this equation. We know that copper, this nitrate to NO from the half reaction in the appendix E, will be a transfer of 3 electrons. However, this copper 1 to copper 2 is a transfer of 1 electrons, so we'll need to balance this by adding 3 here. And then we also need 4 protons for this nitrate reaction, and that will produce 2 waters. So now, first, to calculate the EMF, we first put the reduction, so the nitrate to NO, nitrous oxide, and we get 0.96 from the appendix, and then for the oxidation we get 0.15. So we have a value of 0.81 volts. So now we can calculate delta G, which is equal to negative NFE. In this case, we're transferring 3 electrons. Faraday's constant is 96,485. And our E, which we just calculated, is 0.81. So we go ahead and calculate 2.34 times 10 to the 5th joule per mole. And then for K, we can solve the same way we did before. ln K is equal to delta G over negative RT. So this is equal to negative 2.34 times 10 to the 5th joule per mole over negative 8.314 joules Kelvin mole and 298 Kelvin, which is the temperature we're given in the problem. This gives a value of 94.6, and when we solve for K, we get 1.25 times 10 to the 41. Very, very large value. So now in part C, we're given the reaction of, again, an acidic and basic solution. Chromium hydroxide is oxidized to chromate by ClO minus. So for this reaction here, we have chromium hydroxide wherein it's going to be oxidized by ClO minus, and we're in basic solution. So this produces, we'll leave the subscripts for the second part. So we have chromate, CrO4 2 minus. We produce water and chlorine chloride. So the chromium hydroxide reaction, the oxidation of chromium hydroxide to the chromate, involves a transfer of 2 electrons. The reduction of chlorite involves the transfer of 3 electrons. So we're going to need to multiply the chromium by 2 and the hydroxide and the chlorine by 3. So if we add the half reactions up, some of the hydroxides will cancel from both sides. So we get 4 hydroxides and 5 water. So the EMF, the reduction value here is 0.89 for the reduction of the chlorite, and then the reduction half reaction, the chromium is 0.13, and that gives a value of 1.02 volts. For delta G, we calculate in the same way. We again have a transfer of 6 electrons, Faraday's constant, and our EMF. We get a value of negative 5.90 times 10 to the 5th joules per mole, excuse me. So then we calculate lnk. We get negative 5.90 times 10 to the 5th over our gas constant and our temperature. And we get a value of 238. When we take the ln, we get k is the inverse ln, or the e, 2.25 times 10 to the 1/3. So very, very large.